the inverse square law. Welcome! Today we will demonstrate what the inverse square law is and how it works. First, what is the inverse square law? The inverse square law states that the intensity of radiation is inversely proportional to the square of distance from the source. Let's take a look on exactly how this actually works. Let's say we have a flashlight beam. As we move further away from the wall, the light expands. As we get closer to the wall, the light beam increases and is smaller and more focused on the object rather than around the object. Now, when we talk about calculations and knowing precisely how much intensity we will need in order for the light to actually reach or penetrate an object, we will use the inverse square law, which is the new intensity over the old intensity, which is equal to the old distance squared over the new distance squared. Now, don't panic. This equation isn't as frightening as it may seem. First, let's take a look at intensity and D. D as in distance is. And what do we need to ensure that we correctly use this equation? Now, let's put this equation to the test. If an object has a charge of 4 coulombs at 4 millimeters, what will be the charge at 8 millimeters?
After you plug in the numbers, cross multiply. 64x equals 64, which is 1 coulomb.
Fairly easy, right? In radiology, this law is applied daily. This equation ensures the safety of the patient and radiology technician. Just one step away from the beam can reduce exposure. The barrier seen here helps protect the technician from any scatter radiation. In this photo, adding restriction to the beam in addition to the inverse square law helps reduce the patient's exposure. This diagram shows if you increase 1 Rankine, you decrease the intensity by a fourth. Increasing it to 3 Rankines would increase it by a ninth, hence 3 squared, 1/9. Let's look at another example on how the inverse square law works. New intensity over original intensity is equal to the new distance squared over the original distance squared. If the intensity of the beam is 40 mR at the original distance of 40 cm, what will the intensity be if the new distance is 20 centimeters? Applying the numbers into the equation, we will end up with 40x over 1 squared over 2 squared. This is simplified by reducing the fraction. Once we cross multiply, our solution is finally 160 mR. This is what the new distance would be at 20 centimeters.
Hi guys, I am Sarah. I hope the information used helped to clarify the importance of the intensity and distance. I just want to thank you for watching my presentation and hope it helps you in the future, and good luck.